Hello everyone, welcome to Unfolding the Universe First Light. This is our closing event. Thank you all for being here. It's been a really fun month here at ONX Studio. Very sad to see it close, but we have a ton of great performers and speakers tonight, so we're really going to go out with a bang. Tonight we have Dr. John Mather, who's going to be giving us a talk about the James Webb Space Telescope. Our curator, Maggie Masetti, is here, and she's going to talk about curating the exhibition, as well as curating a bunch of web-themed art projects. So big round of applause for Maggie. But our first act is Astronautica, and they're a group of a cappella singers that are going to amuse us with their beautiful voices and wonderful visuals. So I'd like to introduce them to the stage to get the party started.
Hello, everyone. We are Trio Triumphatrix. My name is Hai-Ting Chin. I'm going to get you used to my acoustic voice because we are going to be singing acoustically. The young person in the front has been asking for several minutes, what is Astronautica? And you are about to, Astronautica is a set of songs that we commissioned in May 2020. Alas, they were never performed live, but they have now become a movie with music by all these lovely women. And we are going to perform 3 excerpts from it for you today. This is us Trio Triumphatrix, except that we have a substitute soprano, the lovely Emily Donato. This is Kirsten Solik. I'm Hai-Ting Chin. And we will be performing for you. Oh dear, that is not good. But you may see it. You may see it over and over again. Apparently. Because I did not get any tech time in here. So, hopefully you will see images from NASA, and please forgive me if you see some of the behind the scenes in between. The first piece is by Jennifer Jolly. These words are those of Heide Marie Stephanischen Piper, which she spoke about this EVA in 2006. And you will hear the words that she spoke as we sing them. Can you be? Mm-hmm. Okay. It is what it is.
Came I can take a breather here. We were, we were, we were, we were pointed, we were pointed at the earth. It was just spectacular, spectacular to look at. Wow! Wow! This is pretty cool to be out here and to be looking around. You could see the earth and you looked at it going by. Wow! Okay, where am I? I realized I'm not as good in geography as I thought. When you look at a map, they always have lines. They always have lines. They always have lines. Always have lines. They always have lines. Always have lines. Borders. Always have lines. Borders. Borders. Easy to tell where you are. Easy to tell where you are. Easy to tell where you are. A whole continent, that's easy. But now you study other features like lakes and rivers and mountains. You look Up above the Earth's atmosphere, you see the stars more abundantly. Up above the Earth's atmosphere, you see the stars more abundantly. But remember right now, we're on a spaceship. I felt connected with infinity. I felt connected with the entire universe. I felt connected. I felt connected. I felt connected.
When I was in space,
I felt connected with the entire universe.
when I was in space, and I feel that connection now, and I feel that connection now, and I feel that connection now, and I feel that connection now.
I felt connected. I felt connected. I felt
When
connected.
I was in space,
I
felt connected with the entire universe. When I was in space, and I feel that connection one day you look up, and I feel that connection as well, and I feel that connection now, and I feel that connection as well, and I feel that connection now, and I feel that connection
as well. I want you to do something for me. I want you to go outside and look up. I do not believe space is a plan B. I do not believe space is a plan B. We get very cavalier about this, but this planet is part of us. We get very cavalier about it, but this planet is part of us. We could not survive without it. We could not survive without it. We have to accept and realize. We have to accept and realize that we have to accept and realize that we have to accept and realize that we have expressed. The reality is this planet is our home. The reality
When I was in space,
I recognized as I looked down, the planet is gorgeous. We
Thank you so much.
Thank you.
That was
Thank you so much
wonderful.
for having us.
And now I'd like to welcome to the stage Maggie Masetti, the curator for Unfolding the Universe First Light.
Thank you so much, Ashley. So I'm Maggie Masetti. I'm a science communicator at NASA's Goddard Space Flight Center, and I work on the James Webb Space Telescope, which is the inspiration for this exhibition. So I don't know how many of you are familiar with this telescope. It launched on Christmas Day in 2021, and its first images came out on July 12th of this year. It is a giant infrared space telescope, and it has an enormous mirror that is made of hexagons, and it is covered in a very thin layer of gold. So the telescope is actually very beautiful, and the gold actually has a scientific purpose. It helps it to reflect infrared light really well. But again, it is just the aesthetics of this telescope were beautiful, and we knew early on that it would be so iconic. So at NASA, we have something called a NASA Social, which is when we invite our followers to apply for a chance for some sort of behind-the-scenes experience at NASA. Sometimes it's a launch. And we had an opportunity because they had built the mirrors of the telescope at NASA Goddard, and they were going to face it towards our little observation area. So we had press come, and we wanted to invite some of our followers to have a chance to see the telescope. But because the telescope is so beautiful, and because we thought it would just be a new audience for us, we invited artists to come and apply and have a chance to see the telescope. And so actually Ashley was one of those artists who applied. This was back in the fall of 2016. And we had only room for 20-something artists. And they came and we set up tables, and they sat right in front of the telescope itself, and we had people from the mission come talk to them and answer questions and gave them a tour and let them just soak in the telescope. So after that, most of them went away and then came back with beautiful art. Also, it wasn't just visual art. We encouraged songwriters and poets and every kind of art that we could think of to have represented, and we ended up having an exhibit in early 2017 at NASA's Goddard Space Flight Center. The statue that I think it's going to get moved around, but it's currently in that back room there, is the one that Ashley created for our exhibit. So it has three hands reaching out of the telescope. One of them belongs to Ashley, one of them belongs to our next speaker, John Mather, and one of them is another astronomer, Dr. Amber Strawn. So I'll let Ashley talk more about her art, but we really felt that art was just a really good way to reach out to people. I think a lot of people are afraid of math and science and think it's not accessible to them, but it absolutely is. And astronomy and space are very inspirational, and I think art is a wonderful way to sort of bridge that gap and to get people to appreciate the beauty of the universe. So I'm going to let Ashley talk about her experience with that and about what inspired this exhibit.
Thank you. Thanks, Maggie. So we're just going to work on getting some water up here for our next speaker. But hi, I'm Ashley Zelinskie. This is my exhibition, Unfolding the Universe First Light. Do I put it on the other side? Yeah, cool. And yeah, so like Maggie said, this has been like 7 years working with the Webb team. Couldn't be happier to be working with them. They're all amazing, inspirational people, and like she said, the telescope is gorgeous, and the first images were gorgeous, so not intimidating at all for an artist. But I want to thank my amazing team that helped make this possible. The first light images only just came out July 12th, so most of the work that's in this exhibition has been made in under 3 months, which is a crazy feat. So thanks to my team. Round of applause for my team. So I'm going to introduce our next speaker, but after that we're going to get everybody to move over to the bar area, get a glass of wine, and we're going to set up the exhibition back the way it was. We'll put all the sculptures in the main area, and then we can start getting people into the VR headset. The VR space was created over the pandemic because we couldn't get together, we couldn't spread the great news about the Webb telescope and that it was going to be launched on Christmas Day. So Maggie and I cooked up this crazy idea that we would make a virtual reality world and invite people to attend virtually. And so everybody showed up as little tiny avatars. and we hosted events for a few months. And actually, John, our next speaker, was came and gave a talk in VR. So you guys can all check that out after the talk. But I'd like to introduce Dr. John Mather. He is the Senior Project Scientist of the Webb Telescope and the 2006 Nobel Laureate in Physics. So, John.
Wow, thank you, Ashley. That's a great introduction, and okay. So I cannot follow the poetic vision of these fingers that showed us their ideas and our experience of being here on our little planet Earth. And I've got a title here which I can't actually fully answer. How did the Big Bang make people? I don't know. Who are we? I don't know. And I'll tell you what we're doing to find out. Okay, so on behalf of all human beings, on behalf of all the astronomers that work here, on behalf of many thousands of engineers, my number is incorrect. It actually took 20,000 people to build this great telescope. Now, Ashley told you, and Maggie told you, it's got a great golden hexagon in space. That big hexagon is about 21 feet across. So it's an enormous project to get up into space. It's protected by an umbrella to keep the heat of the sun and the earth off it. And it's a technological miracle. It's a beautiful thing to look at. We were all amazed when we had it in our labs and we could see it close up. And it's a social miracle that we were able to attain the necessary support from our governments in the US, in Canada, and in Europe. Because it turned out to be much harder than people thought it would be, and it took us a long time. I first started working on it, I think it was Halloween in 1995, so almost 27 years ago. So patience is good. Persistence is good. So I just want to give you a little history, reaching back in time. So here's 1946. This is Lyman Spitzer. He was at the time working for the RAND Corporation, which is a government think tank, and an astronomer, and he said, you know, we could build telescopes in space, and we might need them for spy satellites, and we might need them for looking up. Here's Sir Fred Hoyle. He named the Big Bang, and there he is glaring at us. He didn't like the idea of the Big Bang, and he gave it a name that has confused everybody ever since. So if you don't understand it, it's because of him. Not our fault. Anyway, and this is something else happened. I turned up in 1946. So how do we get to be asking these kinds of questions? Well, I grew up on this place. This is a research farm of Rutgers University in far northwestern New Jersey, just a mile from the Appalachian Trail, and it was real quiet up there. So I got books from the bookmobile, and I learned math and physics and played with electronic toys and lenses and mirrors and telescopes. So that's how I got myself going. And anyway, so just a little bit of the personal background. And when I was about 6, my dad said, by the way, you know, we're all made out of cells, and inside the cells are chromosomes, and they control your fate. Yeah, that's pretty weird when you're 6, you say. That gets your attention. So who am I? Who am I going to be? Well, that doesn't really answer the question I was asking, but it's part of the story. So this is where I grew up, way up there in the woods. That was the buildings. That's the little town of Newton where I went to school. Just to say, this is a real human being walking around with shoes and shirts. And so, you know, people treat us engineers and scientists as though we're miracle workers. Well, it is a kind of thing, but we're like you. We just like to do this. So then I moved from Berkeley, California, back to New York to do my postdoctoral position. And there I am. I rode my bicycle to work. That's where I lived. This is upstairs from Tom's Restaurant on Broadway. And supercomputer in those days occupied half a building. So, and it was a big ding. But now, why do we care? Well, Lucretius told us the problem and part of the answer more than 2,000 years ago. He said, and this is a translation, of course, from Latin. he knew of the atomic theory. So he was already working on the question of who we are. And so this is not so different from what we would say today. He knew about things being made out of small parts. He knew about things changing with time, make small things grow, stick together. This is a precursor to knowing about atoms and molecules and DNA. And then after they get old and tired, they wear out and they fall apart. And notice he also even mentions linguistics. We name things. We say, okay, that's a John Mather. That's a house. So they were onto it pretty well. But now scientists have a different version of this story. How did we get here? We have a story about quantum mechanics that tells us that atoms and molecules have shapes because of the waviness because of the waviness of things. We know the universe is expanding, and it was smooth and hot when it was young. We know it's unstable, and this is a mysterious thing. Nobody honestly knows what made that happen. We have plenty of mathematics. We have plenty of evidence. We know it's happening, and then the next big question is, how does it reorganize into us? Because here we are, we're very complicated. Each of us is made of 30 trillion cells, and each of them is complicated. So how did that happen? Honestly, we're working on that, but I can't tell you that answer. So anyway, while I was up there at the Goddard Institute up on 112th and Broadway, I proposed with my buddies that we should build a satellite to measure the Big Bang. So here it is, and it's a satellite in outer space. It's still out there. It took us 15 years to launch it. I never thought it would work, that we'd send in a proposal and young people headed by a postdoc. That was me. They'll never choose us. But they did like the idea. So it worked. We measured the Big Bang. So a few years later, I went off to Stockholm and got a Nobel Prize for that measurement. So I showed my graph everywhere all the time. And there I am with the king receiving my diploma. So it's pretty cool. So now we thought, well, we know what the universe was like when it was young. Well, what happened then? Well, soon after the COBE satellite, that one was launched, the Hubble Space Telescope was launched, and there it is, looking big and beautiful in space. And anyway, it's still up there. It's working beautifully because astronauts have been up 5 times to visit it and upgrade it. And as far as we know, it could keep on running a good long time yet, especially if we're able to boost up the orbit one last time. So they took pictures. And this is one. This is a picture of something they called the Hubble Deep Field. They pointed the telescope in one empty place in the sky, and one courageous astronomer said, this is important for us to do, but even though there's nothing to look at that people knew about. And they found thousands and thousands and thousands of galaxies, and I don't know if you can see it very well on the projector. It is just a gorgeous picture, and astronomers looked at it and said, thank you very much, it does not answer our question. What happened to make the galaxies grow? What's a galaxy? It's 100 billion stars, more or less, held together by gravity, orbiting a common center, and they formed, according to this picture, they were fully formed by the time this picture can see them. So, in other words, astronomers said, please build us another telescope that can look farther back in time to see what were galaxies like when they were younger, when they were just growing out of the primordial material. So, okay, please build us a telescope. So here's the great James Webb Telescope with a few words to describe who built it. There's the great hexagon over there. It's gold, as was mentioned. The people that built it are NASA, Europe, and Canada, and our big contractor is Northrop Grumman. It is way out there in space, and it was launched on a European rocket called Ariane 5 on Christmas morning. So jumping over that, but here's a picture of the launch itself. And this was so perfect that we went exactly to the place we wanted to go, and so we're going to get 20 years of life. So we are so thrilled with that. We are putting it out to orbit around a place in space called a Lagrange point. It's 1 million miles from here, and it's a perfect place to put the telescope because out there it can be cold and protected from the heat of the sun, the Earth, and the moon. And here's our scary movie. You probably remember we had a Mars landing a while back and we had 7 minutes of terror. This is our 2 weeks of being a little nervous. because this all had to happen by remote control. No possibility of sending a person or an astronaut out there to help it. But on the other hand, we did have control in the sense that we could take every step, see did that work, back up and make us a backup plan if necessary. And we did such a good job in the preparations that we did not need any of the backup plans. So we are thrilled with that, and it is working. It's extremely complicated, and that is what it took to do the science. So it's also why it took so long to build it. Because after you build it, you say, how you know it's going to work? Better test it. Which means this thing that's unfolding now, well, you're going to have to do that more than once. And it's not so hard to get it to unfold, but it's really hard to fold it back up again, like folding your parachute very carefully. And do it right every time. So that's the telescope as it is in space, as it's finally unfolded. So this is the miracle of mechanical engineering, to be able to do this. And the telescope at that point is not yet ready to use because it's not in focus, but it will be. And it took us 6 months altogether to get all set up after this was done. So we were really thrilled when it's worked, and it worked perfectly. So how did that happen? Because we tested, and tested. So I'm sorry we didn't test the PowerPoint first today, but that is our lesson for everyone. Test and test. So, okay. So we have various reasons why we're going to do this. We're going to talk about why observe infrared light. Number one, you see different things. Here's a star being born in this cloud, is surrounded by dust. So why is there dust in space? Well, it's previous generations of stars put out carbon and silicon and oxygen, and that makes sand. And so anyway, there's clouds of dust in space, and it turns out to be that's where stars are being born. If you had infrared, you could see through the dust cloud. So this is the infrared capability of the Hubble, and you can see the star inside, sending out jets of material. And this is a star being born. And so there's inside, though we can't barely see it yet, there's a cloud of material orbiting around the new star, and there are jets coming out from the north and south poles. So pretty cool as part of our story, because we think the sun did that too when it was young. Why else make infrared observations? To see things that are not warm enough to emit light all themselves. So this one's called a planetary nebula, just because it looks like a planet, but is not. And this is a star that is actually double, and it's in the process of destroying itself. Material is coming out from the surface because it's old, it's run out of fuel, it's unstable. And on the right-hand side, you can see the center one is actually double. There are two of them in there, and the redder one on the right-hand side is actually the one that's in the process of blowing up. So a little bit magnified image there, you can see what's inside. So astronomers want to know, how did this work? So right now it's beautiful pictures time, but we will have numbers, and we'll say this is exactly how it works. We'll make that imaginary movie for ourselves and say, yeah, we think we actually know how that happens. The third reason is because space is expanding, and this thing that Fred Hoyle confused us about, the expanding universe, space is expanding as far as we can tell. So distant galaxies appear to be rushing away from us very rapidly, so rapidly that we receive infrared light when they send out ultraviolet and visible light, which is shorter wavelengths. So the light's wavelength has been stretched. So okay, so that's what happens. And so need a telescope to receive infrared light in order to see the first galaxies that grew from the early universe. So here is our first one. We took this picture, and I think this is the basis image that Ashley has used for so many pictures here. This is a star called it's a place called the Deep Field. Again, we pointed the telescope in one direction for hours and hours, but it's a lot quicker. This is hours and hours versus weeks and weeks for Hubble. And we saw galaxies that have never been seen before. So some of them also look kind of weird because they're stretched out. They're little arcs and bits. Even I don't know if do I have a pointer here? Not really. Anyway, up there in the upper, this is a star in the middle. The spikes sticking out. This is a nearby star, and so those spikes don't mean anything except light's a wave. The big bright galaxies, this bluish one here in the middle, has so much gravity that it's able to actually bend light and focus light from the more distant galaxies, so we have an extra lens for the telescope. A natural lens produced by gravity's effect on light. So we've used that to magnify distant galaxies, and we see strange things, and that we see farther away than we could ever see without help of that lens. So, okay, come on, computer. You were working. So what's a spectrum? We're going to spread out the light of these stars and galaxies into a spectrum. So a spectrum is just a rainbow. Spread out the light into the colors. Oh, come on. Spread the light out into the colors in order. So humans see these these colors, but equipment can see many, many more colors. By the way, when we show you a picture in color, we have to make it up. We're going to make up a color so you can attach meaning to what we're going to show you, but of course you could never have seen it. So longer wavelengths are infrared, and radio, and microwaves, and things like that. So a Webb telescope can pick up light that you can't see, and that's why it's important. We can't see it from the ground, we can't see it with a Hubble, and we can see it with a telescope. So we spread out the light, and here's an example of one thing. There are galaxies in there which are not only magnified by that natural lens that Einstein gave us, but also sometimes we even get 2 or more images of one thing. So we spread the light out into a spectrum, and we can now analyze the chemicals that are in that galaxy. And so we confirm not only are these 2 little arcs the same galaxy, imaged twice by that lens that nature gave us, but also they have the same chemical constituents of oxygen and hydrogen. So we're hunting for the most distant galaxies we can find, because we look back in time by looking at the things that are as far away as possible. So we find the little red specks, and you can not really see them on the projector here, but find the little red specks, magnify them as much as we can, and spread out their light into a spectrum to say what's in those. So we get the chemistry, and we also measure how fast they're going away from us. So do it some more, and you can even see other chemicals, like neon. So where do all these chemicals come from? Well, the early universe gave us hydrogen and helium, and if we want to find the very most distant objects, the first things that grew out of the primordial material, it should have just hydrogen and helium. So we've found these others, and they're pretty cool, but they've got oxygen and neon in them, so they're not primordial. So working on that. Sometimes we magnify even more. There's a picture on the right-hand side is called a sparkler galaxy, because we're seeing globular clusters, which are hundreds of thousands of stars together. Here is a thing called Stephan's quintet. It's been known forever. What we're seeing actually are 5 galaxies. 4 of them are near each other and they're in the process of colliding with each other and merging together. The 5th one, this middle one on the left, is actually separate and much closer to us. So the point of this one is we can begin to see what happens when galaxies collide. So stars are small, they run right past each other, but the gaseous material is not, and will actually collide with other gaseous material from another galaxy. So when they collide, they make new stars. So that's what we're seeing here. Also, the top one actually has a black hole in the middle. So how do we know? Well, it looks like a star, a very, very bright star, but if you spread out the light around it, you see, well, it's not a star. Why? What can you see? Well, everyone knows things only fall into black holes. You can't see a black hole. So what we do see are hot material falling in. It gets compressed on the way in. So we can spread out the light again. We see this one's got iron going around it. And we can even see the shape of the clouds that have iron in them. We can spread out the light some more at longer wavelengths, and you say this quasar, this black hole, has sand grains orbiting around it. So why do we care? Well, that's a sign that new stars are being born, and they're going to fall in too after a little while. So this is a part of our story about the black holes. Why do we care about a black hole? Well, there's a big one in the middle of our own galaxy, and it affected our history and prevented the formation of life anywhere nearby, we think. So anyway, fortunately, ours is not active at the moment. Here's a picture that's beautiful. This is a galaxy which has had a collision. The little galaxy in the upper left went flying right through the center of the big one in the right. And so what it do? Well, it made a splash. And the splash is new material forming new generations of stars and stars, owing to the disturbance that they felt. Here's a galaxy that was reprocessed by an amateur image processing specialist. Her name is Judy Schmidt, and she lives in Modesto, California. So she's not an astronomer, but she's able to find the patterns that mean something to us. So here's a galaxy which looks like it's a slice of a sponge. So how does that happen? It means that the big empty spaces, which really are empty, have been cleared out by the pressure of the hot gas that's produced when a new star burns. So you get enough hot stuff, it'll push the material away. And then you'll get new generations of stars being born on the outside rim. So this is another part of the story of formation of stars. Here's a picture called the Carina Nebula. It's one of our most popular pictures. You'll see it in posters everywhere. Why do we care about this? Well, number one, it's beautiful. Number two, it's a story of the Cosmic Recycling Center, where old material that's been enriched by wind, carbon, and oxygen, and nitrogen, and sulfur, and all the things that we see around us, it's being turned back into a new generation of stars. So some of them we see growing in here. Some of them up at the top have already been formed, and they're really bright, and they're sort of burning off the surface of the material that they grew from. So inside we see little weird things like this one. This is a new star being born. You can see it's got two tails. Again, the two jets of material that are coming out from that one are being blown past it while there's a wind blowing past that object. And honestly, we don't know how to figure this out yet. There are many, many numbers you could make about it, and we can only just begin to tell you the story. Here is another example of one. There's the one on the right is another star with new jets coming out, and you can see the wind is blowing one of the jets around it. Oh golly, how does that, what do we mean? We don't know how to interpret this yet. We've been looking in the solar system. Of course, everybody knows Mars is a place that could possibly be alive, or we know it had water. That's a good sign. So anyway, we point our telescope at Mars, and we're just learning a little bit about Mars from this that we didn't already know. But we did get a spectrum of Mars to see, well, what's in the atmosphere of Mars. And so we confirmed what we knew already. We got water and carbon dioxide in the atmosphere of Mars. It's not very much water, but you could capture a little bit of it. There's even a little bit of carbon monoxide, which you could capture if you tried, and if you could get some oxygen, you could use the carbon monoxide as fuel. So the picture doesn't show that we have oxygen, but there is even oxygen. There's free oxygen in the atmosphere of Mars, just not very much. We attacked an asteroid. You probably knew that. It was called the Double Asteroid Redirect Test. So we found an asteroid that had a companion, two asteroids orbiting around each other. So we said, well, we'll hit one of them and see what happens. So indeed, we threw a big chunk of metal into the asteroid. We wanted to see how much would it move, and would it disintegrate, or what would happen. So we watched it with the Hubble, we watched it with the Webb telescope, and dust did indeed come spitting out. So it's something that is part of our planetary protection program. We want to know how to keep those asteroids from killing us. So the ones that would kill us are pretty rare, and we have found most of them, the big ones. The little ones are hard to find. So we're still working on that. Congress said, NASA, you better do this. So we've been looking in the solar system. Here's Jupiter, as you've never seen it before. The great red spot doesn't look red because, of course, we're making up these colors. At the top and the bottom in the north-south poles, you see that Jupiter has auroras. They're always there. They're very bright, and we can see them from here, even 400 million miles away. So we're interested in Jupiter because it's a wild and weird place, but also it has a satellite that might be alive. This is a satellite Galileo himself discovered in 1610. And we sent a probe out there called Galileo, and it took a picture, and it looks like this. There's a surface of ice, and there are brown cracks. And more recently we discovered with Hubble telescope that water comes spitting out occasionally from the cracks. So, so there's an ocean under the ice. Could it be alive? Well, maybe. How are you going to know? Well, the next step is send a probe to fly through that water and see if there's any organic molecules in there. We're going to be watching it with a Webb telescope also, same reason. We will observe this one. This is a satellite of Saturn. There's a geological map on the right-hand side that we made when you sent a probe out there a long time ago, 2 decades ago. We landed a probe on the surface. We got pictures of the rocks. The rocks are probably ice. We're going to send another probe, and we're going to land with a quadcopter this time. And we're going to do chemical analysis and hunt around because it's got geology, interesting geology, lakes and rivers of hydrocarbons. That is to say, methane and ethane that you would be able to use for fuel here on Earth, but maybe over there it might even be the basis of life. It'll be interesting to know. We watched other planets. Here's Neptune. It has rings as well as satellites. Right now, I don't know anything much we can tell you quantitative from this because we're just beginning to understand what we're seeing. We are looking at other planets. Now, this happens pretty often. A planet goes in front of the star. And we've got a catalog of about 5,000 planets that do this. So some of them are not too hard to study. And so we have them on the list. We've got about 5 dozen planets we're going to examine in this way during our first year with the Webb. So, well, okay, so you can tell that the planet is there because it can block some starlight. If the planet absorbs more light at one wavelength than another, that's because some starlight is going through the atmosphere of the planet on its way to the telescope, and you can do a chemical analysis. So this is our hope, one of these days to be able to do this. So imagine there's a little Earth out there with an atmosphere like ours. Imagine there's a star behind it. Some of the light's going through that atmosphere, and how much light is being blocked at each different wavelength. So the different chemicals show up at different wavelengths, and we'd be able to tell you, if this works, whether that little planet has an atmosphere with water. That's what we hope for this time. If we get better at it, maybe you could see carbon dioxide or oxygen. Oxygen we care about a lot because it's here on Earth, at any rate, is produced by living material. So that's hard. We will hope to tell you in a while whether any planets have an atmosphere that we can see that are anything like Earth. Right now, we haven't been able to do that, but we have tested the method on a very big, bright planet, which maybe we should call a steam planet. It has water, it has a lot of water in the atmosphere, and we're not surprised because we knew we should look there, but at least we know the technique works. So in a few months or years, we might have something to tell you about whether planets exist around other stars that might be like Earth. Not easy, but so far, but it's really important. So coming back to who are we and are we alone? Well, my personal opinion is there's life elsewhere. I think there would be life wherever there is something liquid, water. But do I know that? No, of course not. So right now our step is, where could there be liquid water? And after that, is there any possibility of oxygen? So lots of ways you can keep up with us, but we've got our social media, as you mentioned. We are online with websites. If you want to know what we're doing every day, Google JWST images and you'll find us. So something new every day or every week. So maybe stop and have questions. But anyway, thanks so much for coming to hear this story. And I'm sorry I can't really tell you the answer to who are we.